something completely wrong, so you can just interrupt me and say, no, this has to be done differently. And please ask questions as soon as there's anything unclear. If there are too many questions, we have to organize it somehow, but I think it's probably better if you ask questions as soon as you have some. So the title of the talk is Asymptotics of Cheeger constants and unitarisability of groups. And everything I will talk about is joint work with Maria Gerasimova, Dominic Gruber, and Nicolas Monod. And the outline of the talk is, I will talk a little bit about amenable groups, not very much. Then I will introduce this space of Littlewood functions, which will play an important role. I also talk about unitarisability, and then I will give some constructions of groups that are almost amenable in some sense, and provide interesting examples for this this Littlewood coefficient that I will introduce, which is a numerical invariant. So, but let me start very slowly and talk about amenable groups just for a second. So amenable groups, I think you probably all know that. I can be very brief about it. Amenable groups are those which admit large sets which have a small boundary. And more precisely, if you fix a finite set S, let's say it's a generating set, but could be any set, then you want to have a finite subset of the group so that the boundary of that set is smaller than epsilon times the size of the set. Where the boundary is, there are many definitions of the boundary, but it will be important for later use that I fix one definition. And it's really the edge boundary in this sense. So I'm counting all the edges that are leaving my set F. So one end of the edge is in F, and the other end of the edge in the KD graph is outside of F. So it's in some sense, sometimes it's called the edge boundary of the set F. And well, it's well known solvable groups are amenable, non-abelian free groups are not amenable. So there's like a dichotomy in the world of groups, and there are also many characterizations of amenability that you have probably all heard of. A group is amenable if and only if there exists an equivariant or invariant mean on the space of bounded functions on the group. So it means that if you shift your function, it still gets the same mean. And whenever the function is positive, then also whenever the function is positive, although the mean has to be non-negative, and it's somewhat normalized. So this is all well known. I think there are just various characterizations of amenability which are useful in different situations. This is my picture of the zoo of finitely generated groups. So it's not the final picture, but it captures all kinds of different aspects that can occur in the world of finitely generated groups. And what I'm interested in this talk is basically the passage from finite groups to amenable groups, and then to non-amenable groups, and maybe to very important for us, this possible potential class of non-unitarizable groups, which I will explain on the next slides. So what I will introduce in this talk is a numerical invariant that one can associate to any group. And it's a numerical invariant that somehow sees the passage from finite groups to amenable groups to non-amenable groups. And what is really important about it is that it's not trivial in the sense that it only takes like 3 numerical values, like 0, 1, and infinity, which captures finite amenable and non-amenable groups. It really takes more values, and these values that it can take in between amenable and non-amenable groups, we think of them as some sort of a numerical measure of how non-amenable a group is. And we think that it will have more applications, and maybe it will have applications to the study of these so-called non-unitarizable groups. But I will explain all that on the next slides. So this is the previous slide, and this is the next slide. So I will say a few words about uniformly bounded representations. And the setting is the following. I have a group gamma and I have a Hilbert space H. And I consider linear representations of this group on the Hilbert space. And usually one studies unitary representations, so that seems most appropriate. But we will only study representations which are unitarizable, which means that the representation is conjugate to a unitary representation. Right, so there's some bounded invertible operator that conjugates it to a unitary representation. So it inherits, of course, some properties from the unitary representation, and one of its properties is that it will be uniformly bounded, right? The supremum over all the group elements of the operator norm of the operator, this will be bounded. And that's completely trivial to see, because if pi is indeed conjugate to a unitary representation, then we can estimate its norm just using this inequality just by the norm of the operator and the inverse of the operator that you're using to conjugate your unitary representation, right? So it's quite trivial to see that such representations are uniformly bounded. And it's a very natural question to ask about the converse. So what is it true that all the uniformly bounded representations of a group on a Hilbert space are unitarizable, right? So that seems like a natural question once you have made this observation. And there are a few facts that are sort of known from linear algebra or from finite dimensions. So for example, if you have a bounded subgroup of GLNC, so like the image of a uniformly bounded representation on the finite dimensional Hilbert space, then that will be conjugate, then this will be conjugate to a subgroup of unitary matrices. And the argument uses a few facts that are really finite dimensional. And the first observation is that every bounded subgroup in this situation is precompact. And the closure is a compact group, hence. And every compact group is contained in a maximal compact subgroup. And all the maximal compact subgroups are conjugate, and UN is one of them. So that means that every bounded subgroup can be conjugated into UN. That's exactly a positive answer to the question that we were asking in finite dimensions. And so now what's key in that whole problem is what happens if you're acting on an infinite dimensional Hilbert space, right? So that's a more complicated question, right? And you can check that almost all the implications that I have been using is either not true or is completely unclear in infinite dimensions, but most of them form interesting questions. So what about infinite dimensions? So again, if you impose some finiteness condition, if you, let's say, you study a finite group, then that will be unitarizable. Right, and what's the argument? You just average your inner product over the finite group, right? You average the inner product over the finite group, and then you have an invariant inner product, and hence, without changing anything, you will have a unitary representation. That's kind of trivial. That has been well known and studied, I mean, more than 100 years ago, and used in the representation theory of finite groups a lot. But what about infinite groups? So we are interested in infinite groups. So the first non-trivial theorem is now more than 70 years old. That's the theorem of Sekefal-Vinod, who studied the situation of one invertible operator with this boundedness condition. So this exactly means that you have a uniformly bounded representation of the group of integers. And what he proved is that this operator is now conjugate to a unitary operator. And that exactly means that the group of integers is unitarizable. And what's the proof? So the proof is not very complicated. So you consider kind of averages of your operator in the following sense. And then you define a limit in, let's say, the weak operator topology that will again now be a bounded operator that you find. So you're using the uniform boundedness of the operator to see that this sequence remains bounded as a sequence of operators. So you have to have a weak operator topology limit. And then it's an algebraic calculation to see that this is now indeed a unitary operator. So the proof is using averages. It uses almost invariance. And so by the time a lot of people knew about amenable groups, and this proof was then very soon generalized by various people to all amenable groups. So if you know the definition of an amenable group, I have shown you the definition, you see that the same proof essentially applies to amenable groups. And you can phrase it a little bit differently. You can write down a concrete norm using the average, using the invariant mean. So you just average the squares of the norms of the vector that you get by shifting by the group element G. And by the nature of the Hilbert space norm, the result that you're getting here will again be a Hilbert space norm. It just satisfies the parallelogram identity on the nose, very easy to check. And by the uniqueness of the Hilbert space as an object, that object that you're getting now will be isometrically isomorphic to the original Hilbert space. And that exactly tells you that you're getting an equivalent unitary representation on the Hilbert space you were starting with. Right, and now we can ask maybe a more precise question, because we have now encountered a reason why a group is unitarizable. And this question was raised by Dixmé, it's now 60 years ago at least, which asks, is unitarizability a characterization of amenability, right? We have seen all amenable groups are unitarizable, but is the converse true? Are unitarizable groups automatically amenable? So when he was asking this question, it was not clear that amenability, or at least some strong negation of amenability, would be an obstacle. But I guess he had the correct feeling, because it was shown soon after that the free group on two generators is not unitarizable, right? So there are concrete examples of, I mean, there are various arguments that one can make, and by now there are really concrete examples of representations of the free group on two generators which are not unitarizable, using the Poisson boundary or using the Katy graph in some form. And as a corollary, one can also see that every group that contains a free group on two generators is also not unitarizable. This is basically just an induction argument. So we see that we are really encountering a strange world. So the question remained only open for non-amenable groups that do not contain a free subgroup, a non-abelian free subgroup, and such groups are really rare. And the first examples were constructed by, I mean, finitely generated by Olshansky, right? So there are examples for which the problem is still open. That's what those examples provide. But one sees that it's really a tough problem, because there will be no natural groups that you could come up with to check the conjecture. However, I mean, this was a problem for a long time to attack this problem, and some people conjectured that maybe Burnside groups of large exponent, which are known to be non-amenable, might be counterexamples. But then there was a theorem by Monod and Osawa where they proved that those Burnside groups are non-amenable. I mean, were known to be non-amenable by work of Adian, but then were also shown to be non-unitarizable under some constraints on the exponents, but in quite a large generality. Right, so it's an interesting problem. I mean, if you look about the root of attack for finite dimensions, you might well wonder what are actually the bounded subgroups in the group of invertible operators on a Hilbert space, right? So what are the bounded subgroups? And maybe is every such bounded subgroup contained in a maximal bounded subgroup, right? That's an open problem, and it's really interesting. It's just, I mean, Christian Rosenthal has studied this problem in some form, and I mean, it's an open problem to answer this question. And there are not many examples of maximal bounded subgroups. How do they look like in general? It's completely unclear. So it's, even though the question is quite natural, this is a problem that does not have a satisfactory answer at the moment. We will use these Littlewood functions to get closer to this problem. So we will not answer any of these long-standing conjectures, but maybe this invariant in the end will turn out to be useful to attack some of these problems. So it's now, I will now say a little bit about this space of Littlewood functions. So the space of Littlewood functions, first of all, it's a space of functions with complex values on the group gamma. So it's denoted by T1 of gamma. And the definition is a little bit strange, but I think one needs a little moment to digest the definition. That's what I want to say, if you haven't seen it before. Because it involves some interpolation of two different norms that you can put on convolution operators. So first of all, what will play a role in the definition of the space of Littlewood functions are functions not defined on gamma, but defined on two copies of gamma, on gamma times gamma. And each such function, so let's say for the moment finitely supported, to keep it simple, or let's say L in some sense in L1, each such function gives rise to a convolution operator, let's say on the space of compactly supported functions on gamma by the usual formula. You just consider this function fi here, you consider it as, let's say, a gamma times gamma matrix, and then it acts on gamma in the vectors which are indexed by the group gamma in the obvious way, right? And as such, you can put a lot of norms on this space of so-called kernels of functions from gamma times gamma on to the complex numbers. And one norm that you can put is the norm that you are obtaining by letting it act on L infinity of the group and take values also in L infinity, right? So this gives you now, let's say, an operator between two Banach spaces, and as such an operator, it has an operator norm, and that's denoted by the norm and then infinity to infinity. So I'm fixing the two norms on the Banach spaces, on the domain and on the codomain, and then I obtain an operator norm that is denoted like this. And similarly, I might act on L1, taking values in L1, and this gives me another norm. And well, now comes the definition. A function is a Littlewood function if you can consider it as an equivariant kernel by making it artificially taking two arguments, and then you can decompose it in a non-equivariant way into one kernel which is bounded from infinity to infinity, and another kernel which is bounded from 1 to 1, right? Okay, that's a strange definition. But I think we will see that it's a quite useful definition. I mean, if I say it's strange, I don't mean it's not a good definition, it's an excellent definition, but it might seem strange if you see it for the first time. Was there a question?
This is definition by Littlewood.
No, this is, I think you're asking a good question. So is it a definition by yourself or by Wysochansky, or a paper by you, yourself and Wysochansky? Is that the source where it appeared in the group case?
Okay.
You will be able to answer this question best, I think.
I think that was on our seminar. This was Professor Pełczyński suggested. Okay. This connected with Littlewood inequality, and this is natural, and not T1, but T2 is more natural. That means that because this is row and columns, you decompose that invariant matrix. F1 is like row that you calculate norm in the row and then in columns. So now it's related to row and columns operator spaces.
Exactly.
Okay, but this is Littlewood inequality, and T2 is important, and then gives you multiplier of Fourier algebra, completely bounded. Okay.
Thank you. So we define this T1 norm now exactly as the infimum over all the sums of the norms that we can achieve in this decomposition. So it's some interpolation of norms that you can put on the kernels, and then you restrict to the equivariant operators. So that's another way of seeing this space of operators. Okay, so let's look at some examples. First of all, it is fairly easy to see that L1 of gamma is always contained in T1 of gamma. And it was shown by Wysochansky, if I'm correct, that this equality in this inclusion characterizes amenability. That's one of the first main results about this space and how it relates to amenability and non-amenability of cubes. Okay, so we will keep that in mind. And now look at the opposite side. Now look at the free cubes. So let's take the free cube on n generators. So let's say it is generated by A1 through AN. And let f be the characteristic function of the generators and their inverses. So that's a natural function to consider. And so now we want to compute the LP norm of this characteristic function. That's very easy. It's just like this for obvious reasons. And we also want to compute the T1 norm. And I claim that the T1 norm is less or equal to 2. And I will argue that this is the case on the next slide, but let's first see some consequence. If we note that the free cube on n generators is contained in F2 for any n, then this implies that T1 cannot possibly be contained in LP of the free cube for any p less than infinity. Right, so if it was contained, then it would be contained in such a way that the norms are bounded by a constant, right? So that's just easy Banach space theory argument. But then looking at this, looking at these inequalities, looking at these these two computations, you see that this cannot be the case, right? So once we have argued that this inequality, this one is really satisfied, then we have seen that for the free cube on two generators, really something completely different happens. It's not equal to L1. It's not even contained in LP, right? Okay, so that's a completely opposite behavior, and we will make well, kind of use of that dichotomy in order to define the invariant that we are interested in. So let's look at the geometric picture. So that's the Cayley graph of the free cube on two generators. So let's just argue for the free cube on two generators. And we have this, this function f now, and we want to decompose it. So the function f, it's a convolution operator, it's equivariant, and it's just basically some multiple of the canonical Markov operator corresponding to the random walk. And so each edge of that Cayley graph has to appear somehow, and F1 and F2, they allow us to make a non-equivariant choice. Which edges do we put in F1 and which edges do we put in F2? So let's make that choice. It's not very complicated to do it. Once you know it anyway, you can write it down easily. So we define F1 of xy to be 1 if x is 1 longer than y, and we define it to be 0 in the other cases. And what I claim is that with this definition, it is not complicated to see that this is of norm 1 from L infinity to L infinity. Because what does it do to an L infinity function? So you have an L infinity function on the cube. This operator, it will just move the values outwards by 1, right? It moves the values outwards by 1, and that's clearly not changing the L infinity norm, right? And so there are, of course, a lot of edges missing, and these are exactly the edges that we put in on the other side, where we consider the case. It's now just exactly the opposite case, where basically the first variable is now one longer than the second variable. And this operator, which is just the transpose of the first one, that's now bounded by norm 1 from L1 to L1. Why? Because you're just moving all the values 1 inwards, and that's not changing their sum, right, if they are positive. So you see from the definition, this decomposition, it just gives you that the norm of this in this space of T1 functions is bounded by 2, right? And combining this with the computation that we did on the previous slide of the P norm, we now obtain that this inclusion cannot hold. So T1 is not contained in LP for any P. So that's a computation that we did for the free cube on 2 generators, but the same computation holds for any cube that contains the free cube on 2 generators. And so now we turn that into a definition now, these 2 observations, and define very courageously the Littlewood exponent of our cube gamma to be the infimum over all P, so that T1 is contained in LP of the cube gamma. Right, so some people might wonder, why did we take LP and not some other completion of the cube gamma or of C0, of the compactly supported functions? But let's just stick to LP for the moment. We will see that there are a number of interesting results that that can be proven about this Littlewood exponent. So first of all, we can characterize finiteness of the cube by the Littlewood exponent. That's fairly easy to see. The second thing is that's not quite the result of Wysochansky on the nose, but it is possible to characterize amenability of infinite cubes also by the Littlewood exponent. Being equal to 1. So now comes the interesting connection to unitarisability. I will mention the exact authorship of this result in a few seconds. So it's due to Božeko and Fendler that the Littlewood exponent is less or equal than 2 if the cube is unitarisable, right? And well, considerable efforts I think have been made to prove that it's actually equal to 1, but right, or is smaller than 2 always. But since they have failed so far, we are kind of hoping that maybe there is some world of cubes that have Littlewood exponent in between 1 and 2, and then they would give rise to maybe some interesting cubes which are unitarisable but not amenable. But note, this is only an if, it's not an if and only if. So even if we find a cube which has a Littlewood exponent, let's say of 3/2, it's not necessarily unitarisable. Only the other direction is true. If it is unitarisable, then the Littlewood exponent is bounded by 2 and then has to lie somewhere in between 1 and 2. And we don't know exactly where it is at the moment. So what I think is maybe the most surprising new result that we have found is that there is actually a cube which has a Littlewood exponent which is in between infinity, which we will see is a character is most of the time the case. It's certainly the case if it contains a non-abelian free subgroup. But there are cubes which are kind of on the edge between amenability and non-amenability, and they are kind of in between the two concepts in a rather strong sense, namely in the sense that that this Littlewood exponent does not take the value infinity, and still the cube is non-amenable, so it can also not take the value 1. I already said that in all the cases that are kind of more classical, if you contain a non-abelian free subgroup, then the Littlewood exponent is actually infinity. And then there's also a result that says that this is not a characterization of containing a non-abelian free subgroup. So we have also examples of torsion groups which have a Littlewood exponent which is equal to infinity.
But
so
is it true that for each number between 1 and infinity, there exists gamma with given lit of gamma?
That's an open problem. So far we have constructed just one group with this property, and our construction can probably be changed so that we, let's say, have countably many different values, but we cannot. I mean, if you give us an interval, we cannot give you a group which has a Littlewood exponent in that interval. So we don't have, for example, an example of a group which has a Littlewood exponent in between 1 and 2. That would be the most interesting case, at least if you are interested in non-unitarisability or unitarisability, but we cannot construct such a group for the moment.
Which class of group you have when Littlewood is bigger than 2? You have concrete example?
Yes, we have a concrete example. I mean, it's not so concrete in some sense, but it's. I mean, that's part of our paper that we wrote down the construction of such a group. I will explain more about it later in the talk.
As you said, between 1 and 2 is open, if there exists such.
Yes, exactly. It's unfortunately it's still open. Yes.
Thank you very much.
So let me first say a few words about the amenable case. So I already said that there's this theorem of Wysochansky, which characterizes amenability by the equality of these two Banach spaces. And this doesn't quite prove that Littlewood exponent equal to 1 implies amenability, because a priori this Littlewood exponent is an infimum, right? It's an infimum of numbers, so it could be that it's contained in LP for all the p's bigger than 1, but it's still not contained in L1, right? So such things, such functions, of course, exist, and we have to deal with this problem. And so what we are using is the following lemma that also goes back to Wysochansky, at least I think, goes back to Wysochansky. And another result that I've proved in a completely different context, which gives, well, some bounds on the norm of Markov operators in non-amenable groups. So what I proved is that if the group is non-amenable, then there exists arbitrarily large finite sets. You can take them to be generating sets of the group gamma, so that the Markov operator from L2 gamma to L2 gamma is bounded by some expression that in some sense is uniform in S, right? So this was not known before. I think Kate and Tatiana worked on that problem for specific groups, but in that generality it was not known. But it implies, of course, in combination with this inequality that you see up here, you have now a way of bounding the T1 norm from above by some expression in I mean some power of the size of S. And since the LP norm can be computed concretely, this implies by a little calculation that I will not do now, that T1 is not contained in LP for some P which is really, really small. So I mean, I have no control, no explicit control on this epsilon. So I also have no control on the P here. but it at least means that it cannot be, if the group is non-amenable, it cannot be that T1 is contained in LP for all P's bigger than 1, right? There will be some gap. And that's exactly what we need in order to prove that the Littlewood exponent can only be 1 if the group is really amenable. So by the way, I have a question. So how long is my talk?
It is 50 minutes usually, but it can be longer.
Yeah, so that means something like 15 more minutes, 20 more minutes.
That sounds right, yeah.
Right. So I will now give a geometric calculation of the Littlewood exponent. And that's somehow really where
Andreas, there is a question from Michael de La Salle.
Yes.
In the messages.
Actually, this question was answered. It was the same question as Marek's question, and so Andreas answered it.
Oh,
okay.
Sorry.
Excellent. So what makes this Littlewood exponent useful and invariant is that you can compute it in various ways. So you can either compute it from its definition, or you can try to compute it. So both ways are not easy, but there are two essentially different ways that are allowing you to compute it. And the other one is geometric. It uses some form of isoperimetric inequality. So let me recall the definition of the Cheeger constant. So now it will be important that I'm indeed looking at the edge boundary here. So there are variations into literature, but it will be important that in this situation we are looking at the edge boundary, right? For our calculations, this will be important. So the Cheeger constant is defined to be the infimum over the ratio of the size of the boundary versus the size of the set. And using the Cheeger constant, I'm defining another quantity, which I will call the relative maximal average degree. So it's expressible in terms of the Cheeger constant, but it has another, because it's kind of just concretely defined in terms of numbers of edges and so on. You can write it more concretely as the supremum over all the finite subsets, and then you take the Cayley graph, you restrict the Cayley graph to your finite subset, you look at the induced subgraph on that finite subset, and you just count the edges. You count the edges, and you divide by the number of edges that you could see like maximum, right? So that's the maximum number of edges that you could possibly see if you look at F and then all the edges that are leaving leaving the set F, right? So you're normalizing it in some sense, and so that's in some sense. I mean, if you would only look at the nominator, then it would be the maximal average degree in some sense, and it's also relative to S, so we call it the relative maximal average degree. So it's a little bit clumsy, this name, but I think it's useful. And then we want to get rid of S also and take minus the lim inf of that quantity. So I think it's probably very hard to understand what we are doing on this stage, but it will be completely clear once we are looking at a few examples. So let us look at a few examples. And these are the examples. So here are again the definitions of this maximal average degree, and also of the invariant that we extract, which does not depend on S anymore. And let's look at the amenable case first. In the amenable case, if you look at a large invariant subset, then almost all the edges that start in F, they also end in F. And so we see that the number of edges in this induced subgraph, it's almost F times the size of F times the size of S. So you see, when F is very large, then this will be almost equal to 1. And if it's almost equal to 1, then you can check. Logarithm of 1 is almost 0. So you see that this invariant eta that we have been defining must be equal to 0. So let's look at another example. Let's look at the example when gamma is a free group. Then if you take a set F, then the induced subgraph, it will be a forest, or in the worst case, it will be a tree. So you see that the number of edges that are contained in this forest or in the tree are about the same number as the number of vertices. So you see that the edges in this situation, they are behaving asymptotically like the size of F. So looking at the definition of E, you see that F cancels and you are left with S inverse. And then if you look at the definition of eta, you will encounter that eta of gamma is now equal to 1, right? Because you're taking minus the logarithm of, well, S to the minus 1 and so on, you get minus minus, which is equal to plus 1. And so, okay, so in the two cases, you get some interesting invariant. And in general, what we are after is some sort of exponent that captures the following behavior. So we want to have larger and larger subsets that have the property that if you look at the induced subgraph on the finite set F, the number of edges are at least F, which is the size of the set, times S to some exponent alpha. And this is supposed to happen also for all the generating sets. So it's a little bit tough to understand, but I think probably these examples, they can give you a feeling what's going on. You want, well, it's some form of amenability, only that you have this crazy exponent alpha that comes up and it kind of measures how non-amenable the group is, or how it kind of sense how amenable it still is, and so on. Right, so that's our invariant. So that's eta of gamma. And now that's the theorem. Eta of gamma is related to the Littlewood exponent. It's 1 minus 1 divided by the Littlewood exponent. So that's the main result of the paper. And yeah, I think it's really useful because you have this analytic side, this right-hand side, and then you have the left side, which is of completely geometric nature, and you can use information about either of the sides to say something about the other. And we will use exactly this mechanism to provide a group which has a finite Littlewood exponent while still being non-amenable. Right, that's exactly a computation of the right side using some geometric information about the group that we provide using isoperimetric information. Okay, I will skip this with the spectral radius. So now comes, so that's, I will be a little bit brief because I don't want to go over time for too much. But this is the relationship with unitarisability, which is in itself, it's a beautiful argument that I just want to tell you in order to show you how interesting all the connections are between the different analytic properties. So that F be a Littlewood function, so that means we have this decomposition into two non-equivariant kernels. One is bounded from infinity to infinity, and one is bounded from L1 to L1. And now what we are doing is the following. We define a new operator. So we view, so I mean, all the, I mean, F1 is a kernel, so it acts on L1. And lambda of x, this is the left multiplication by x on L1 of gamma. So you can look at the commutator of these two operators. And by definition, so let me just see what I wanted to say. So I guess probably if I want to make this completely correct, this should be 2 here. so this is now obviously bounded from L1 to L1, because by definition F2 was bounded from L1 to L1, and certainly the shift by X is bounded from L1 to L1. But if we compute the commutator, with F1 now, then F1 can be written as F minus F2, and F was an equivariant operator. So we obtain that it's exactly the same commutator, only with the minus sign. And knowing that, you see that the same operator that we studied, this delta X, is now also bounded from L infinity to L infinity, right? So I guess since I changed the definition of delta, there now must be a minus here, but it doesn't change. It doesn't change the argument. So you get operators which are bounded from L1 to L1 and from L-infinity to L-infinity. And by the Riesz-Thorin interpolation theorem, you get bounded operators from L2 to L2. Right? So this is usually harder to obtain, but this way we can get it by interpolating operators that are bounded from L1 to L1 and L-infinity to L-infinity. And so what you obtain is a bounded derivation. So it's not complicated to see that since everything was defined as a commutator, this is indeed a derivation. And using a simple trick, you can now define a representation by just putting the derivation into the upper right corner of a 2x2 matrix. And this will be a uniformly bounded representation. And you can see that if it is unitarizable, if lambda is unitarizable, then it follows that this function f, which is essentially a matrix coefficient of this delta, that this function has to be in L2. Right, so it uses a few more tricks, but it's believable that this must be the case. And so this implies the corollary to Božeko, originally due to Božeko and Fendler, that T1 is actually contained in L2. So that's the argument. If gamma is unitarizable, then T1 is contained in L2. And hence, in terms of our Littlewood exponent, if gamma is unitarizable, the Littlewood exponent is bounded from above by 2. Yeah, and you can try to change this argument at all possible places, and it's not, yeah, we haven't been able to prove that there's a better bound on the Littlewood exponent. And well, Dix-May's conjecture would say that the Littlewood exponent has to be 1 if the group is indeed amenable, but it's not possible to see it using this argument. Was there a question?
So have you an example of such a gamma which satisfy to this inclusion but not amenable?
No, I mean, there are no examples like this. No known examples like this.
This is main problem. Yeah.
So we have our one of the results that I will speak about on the last slides is there exists a p less than infinity, and there exists a group gamma, so that T1 of gamma is contained in LP of gamma, and gamma is not amenable.
Okay.
That's the best that we can do, but we don't get it. We don't get p down to 2. That's not.
Okay.
But that p is bigger than 2, yeah, in some sense.
Yes, our p is definitely bigger than 2.
Thank you.
Right, and so let's try to construct exactly this group that I've mentioned here. So this group we will now construct, or I give some hint on how to construct it on the last slides of the talk. Right, so exactly this is the property that we want to get to. And so remember, there's this relationship with the Littlewood exponent, and this isoperimetric invariant was defined like this, where this was the average maximal, the relative maximal average degree. And so what it means in practice is that for each generating set, and that's now already tough, because for each to do something for each generating set is, well, is difficult, right? For each generating set, we have to find a finite subset of our group gamma, such that the edges in the KD graph, when restricted to F, are still many, in the sense that they are more than F times S to the alpha for some uniform alpha which is bigger than 0. Right, so this is exactly what we have to do, and in order to do it, we have to use all the tools from graphical small cancellation theory, and that is the part that Dominic Gruber took care of. So I think it's some joint ideas, but I think the technicalities are nothing that I'm really familiar with. So how do we do it? So we start with a hyperbolic group, and in our situation, we will assume that it has property T, so that in the end, we can also ensure that the final quotient that we are getting is not finite and is not amenable. But let's for the moment just take a hyperbolic group, and we will define a sequence of successive quotients of this hyperbolic group. Start with gamma 0, next quotient gamma 1, then gamma 2. And at each step, we will put enough relations so that for one more finite generating set, a finite set F exists with the desired property, right? So it's an inductive process, and we enumerate all the possible finite generating sets of gamma, and then sort of one by one, we will add enough relations to ensure the existence of some incredibly large finite set F, which is still kind of reasonably closed with respect to S, in the sense that we have this inequality. There are still many edges that are not really leaving F in some sense, right? So the edges inside the induced subgraph, it's still many in this weak sense, so for some uniform alpha. Of course, the problem really arises by making everything uniform in alpha and so on, but right, so how do we do that? So we look at suitable Ramanujan graphs, and we pick random labelings with our finite generating set. And the point really is that if you have a graph whose degree is D, if you have a graph, let's say you have a graph V, let's say it's one of these Ramanujan graphs, and the degree is equal to N, and the size of S is, let's say, equal to M, then if you randomly label the graph by S, then somehow it will not satisfy any small cancellation condition unless M is really larger than N, a lot larger. But what is important for us, that it's enough to take M to be some polynomial in N. So it's actually just some finite power of N. And this will be exactly the reason why in the end, in the end you get this uniform exponent, right? So this will be exactly 1 divided by the degree of this polynomial P that comes up here. I mean, there are more things that go into it, but this will be essentially the reason why you find some uniform alpha, because in this situation you find some uniform degree on the polynomial that you have to study in order to make this work. Right, so that's what I want to say about the proof. So that's very brief, but the details are really very technical. It's written in the paper, and I hope I can also answer a few questions about this construction. But right, it's using graphical small cancellation theory, and uses all the technology that has been developed in this context.
Is it periodic?
No. The group that we construct is not periodic.
Mm-hmm. Thank you.
So what are the open problems or the perspectives that I would like to mention? Well, first of all, it would be nice to have more examples of groups and to try to like get this Littlewood exponent down more and more, so that in the end maybe you have some chance to get it smaller than 2. So for the moment, it's not clear whether there are any restrictions on the values of the Littlewood exponent. So can it be any real number between 1 and infinity? That's a possibility. Maybe it's restricted in some sense. Of course, it's very interesting if that may be a forbidden range for the Littlewood exponent. That would imply Dix-May's conjecture. Related question, but also very, very interesting, is this inequality actually characterizing unitarisability? So we don't know that. That would also be very nice. And if that was true, then we cannot quite, first of all, it doesn't prove Dix-May's problem, but it's giving you a hint that maybe there is a forbidden range. Because there's a following corollary. So that's the actual corollary, but it depends on the positive answer to the previous question. So if Littlewood less than 2 really characterizes unitarisability, then at least in this interval, there are no groups with that Littlewood exponent. So that relies on a result of Inessa Epstein and Nicolas Monod about the characterization of unitarisability. Yeah, that's what I wanted to say. So I think I made a little bit over time, but not too much. So yeah, thank you very much for your attention. Maybe there are questions. There's a last slide which just has a picture on it. So where is it? Will not show. Okay. Yeah, thank you very much.
Thank you.
Thank you.
Thanks, Andreas.
Possible,
Maybe just
I would like to ask something. Can I ask?
Yes.
So I have some historical remark, because you voted to Dix-May that question, but I study, and everybody should look for the old paper of M.G. Crane, Ukrainian Journal, 1948, when he a beautiful paper, of course, in 48 before Dix-May, when he observed that amenability implies that unitary representation coefficient are completely bounded multiplier, or Hertzsprung multiplier we call, and this of course because unitarisable representation are also a completely bounded multiplier, and that is one of the open problem between this. I showed some times ago that completely bounded multiplier and Fourier state algebra equality is amenability. So if you have no, that is some sense between and Crane result was in this direction. Anyway, so this will be also looking not only for T1, from this context T2 is more interesting. So like anyway, probably if you look for my paper, because Wysochański was my student, and this was diploma thesis when he wrote.
I see.
But we wrote also another result in this direction. Anyway, but I am interested what you mentioned the Monod result that is between 1 and 4/3. So you have so how is this connection with Gilles Pizier? Because he also wrote paper in this direction, but I don't know. He has different constant for not unitarism. Is some connection with your constant? Or?
No, that is very interesting. A very interesting question. Whether he has this similarity degree that he is defining. Maybe there's a relationship between the Littlewood exponent between 1 and 2 and the similarity degree, but we have not been able to prove anything in that direction. But it would be beautiful, right, to see how this discreteness somehow is related to discreteness of the Littlewood exponent.
Do you
have you continuous? Sorry, Michael, please, Michael. Yeah,
Yes.
I'm
I
finished.
think
Okay.
you have an example where you know that the Littlewood exponent is not an integer?
No.
Probably this is,
Other connections with problem which Gromov considered embedding to Hilbert space, group which can't be embedding to Hilbert space, and so on.
Yes, so the group that we are constructing, it's the KD graph contains a sequence of expanders for every generating set. I mean, for every generating set, the KD graph contains a sequence of expanders. So it's in a very strong sense not embeddable in a Hilbert space. So it's really a very bad group in some sense, exactly from that perspective, that it contains expanders, but in all possible ways, for all generating sets, there will be many expanders.
But perhaps there is some invariant in this direction, connected to possibility or non-possibility to embed to Hilbert space with some additional properties. Yes.
Maybe, yes. Thank you.
can I ask, did you have continuous version? Because it's also a natural question, yeah. For continuous group, like SL2R, we know they are not unitarizable, but in this direction, because
Well, we have not studied continuous groups, but I would guess that in the end, it's the totally disconnected case that matters, and then kind of, yeah, I don't see really interesting topological groups for which this problem would be, or would be easier in some sense. Maybe a counterexample exists or anything else exists. So I think it's probably doable. I mean, many of the techniques have extensions to topological groups, but we haven't studied it. So was there a question in the chat, or? Oh yeah, property T groups. No, I think nothing is known for property T groups. Would be very interesting question. Is a unitarizable property T group, is it finite or whatever? Yeah, it's not known.
but maybe Michael de La Salle, you know, connection with the approximation property, because this is, you have some result negative. So did you look for that connection with not unitarizability?
I like both questions, but I do not see any connections. But,
not yet. But also you have in LP, yeah, in LP some sense, completely bounded LP multiplier.
Yes, there are things like this. Ignacio Vergara has results in this direction. But I don't know, I don't see a connection directly.
Thank you. Nice to see in good condition. Yeah. Good.
Thank you very much.
Is this paper available?
Thanks, Andreas.
Oh yes, yeah, it's in the archive.
Oh, in the
And
archive.
it actually appeared on the Journal of Function Analysis, JFK.
So there was some question.
I can send you a link. Sorry.
There was some question about T1 and LP, and P goes to 1, like characterization of unitarizability, or what was the?
Which question?
You were mentioning that there is a unitarizable group. Sorry, I'm not completely sure what exactly I'm asking. I think, I mean, there is a classification of amenability, right? That T2 is L2 and T1 is L1 or something like that. And I guess I'm asking for some sort of unitarizability characterization along those terms, but for P going to some, I don't know, going to 1 or like some approximation.
Well, I mean, I know it's so the only result is the one by Božeko and Fendler that relates this Littlewood exponent to unitarisability, and then everything else would be very interesting if you can bound it by a better number than 2, or maybe.
And we don't know if it's a characterization, right? Like
we don't know that. Yeah. Mm-hmm.
Thanks. Right, I guess we'll thank the speaker again.
General saying is the
Okay,
book of lecture note by Gilles Pizier about unitarisability, something like in this connection with sister algebra more generally. If you have bounded representation of sister algebra, that is connection with amenability. Did you have something in this direction? Or
no.
Okay, groups are the most important, of course.
Yes.
I wonder if Marek can give us citations to his papers.
Which paper?
You mentioned something in Ukraine.
MG Klein. MG Klein, beautiful paper, a homogeneous kernel or something like this. And this is Ukrainian journal, 1948. I read this in Ukrainian, Russian, because this was Russian language. Ukrainian journal, original Ukrainian, maybe it's now translated. Very beautiful paper.
No,
there
this
is
is
3 parts, 1, 2, 3. So and
yes.
that is a lot of nice idea there. And I very much suggest to everybody who studied this problem, look for that MG Klein paper. Probably Professor Wierszyk knows this very well.
Yes, I know very well this paper. This is a classical paper.
Classical.
Yeah, Mark Crane. And by the way, in that time, he has some, how to say, parallel discussion with Gelfand, because just in that time, Gelfand and Naimark constructed the representation theory, and Mark Crane gave another approach to this.
Thank you very much.
All right, I guess we're ending up the meeting, and I'll post this as a video on YouTube channel.
Great.
Thanks, Andreas. Thanks.
Okay. Bye-bye.
Thank you. Thank you, Katya, for inviting me.
Thanks.